So we're going to look at graphs of quadratic functions to start with today. So quadratic functions, remember, are degree 2 polynomials where your variable is raised to the second power. And you can write every quadratic in vertex form, where h is the x-coordinate of your vertex and k is the y-coordinate of your vertex. Your parabola is going to open up if your value of a is positive, so greater than 0, and open down if it's less than 0. And all that relates back to the transformations that we've talked about in the past. So your quadratic functions make parabolas, like little U-type shapes, and you always want to find your vertex first, because you know it's symmetric about that point. So if you think about your transformations, this has a transformation right 4 units and up 3 units from your parent function x squared's vertex, which would just be at 0, 0. So my vertex is at 4, 3. My axis of symmetry that I just drew in that vertical line there is the line x equals 4. And I do need some more points to make my parabola shape. So let's pick some points close to my vertex. If I pick some x's far away from my vertex, the y's may not fit on my graph. So I'm going to go right next to my vertex at 2 and 3. And if I plug 2 into my original function, I get the y value of 1. If I plug 3 in, I'm going to come up with a y value of 2.5. And then I'm going to plot those on my graph. So 2, 1. 3, 2.5, and then I can reflect those over my axis of symmetry and draw in my complete graph shape. We're also supposed to, I did the first two parts, my vertex and axis of symmetry, but I'm supposed to give my domain and range. So in terms of x values, this continues expanding left and right in both directions forever and ever. My range, it goes up to the highest y value of 3, and then all the rest of my y values are smaller than that. So it'll be from negative infinity to 3. It includes 3, so it should be a square bracket. We are going to graph this function by first putting it in vertex form. Right now it's in what's called standard form, which I'll talk about an option to graph those tomorrow, but let me show you how to put this in vertex form. So we're going to do a little completing the square. I like to rewrite it with just y equals instead of f of x, and then if you think about when we've completed the square in the past, we found the number of units that makes our quadratic factor as a perfect square. 7 is not the right number of units to make that happen for x squared minus 6x, so I went ahead and subtracted it over to the other side of my equation, just so it's kind of out of sight and out of the way there. And then if I think about x squared minus 6x, that's not a square, it's a rectangle. So I'm going to cut that negative 6x in half and make the side lengths of my square the same length by having a length of negative 3 units on each side instead. And then to complete that square, my right-hand corner there is going to take up negative 3 times negative 3, 9 square units. So I can add 9 units to both sides of my equation to keep it balanced, and that allows me to factor x squared minus 6x plus 9 into a perfect square as x minus 3 squared. Because if you look at the side lengths of that square, they are length x minus 3. So you could write the area as x minus 3 times x minus 3, or x minus 3 squared. And then, just to put it in vertex form, I'll go ahead and subtract 2 from both sides. It's solved for y. There are a couple other options here if you don't like doing it exactly that way. You could start by just rewriting it with the 7 like off to the side. You don't have to necessarily subtract it. And then think about, okay, to complete that square, how many units would I need to complete the square on x squared minus 6x, because 7's the wrong number, and run through the same thought process for completing the square and go, oh, I need 9 units there. And then you could factor the x squared minus 6x plus 9, just ignoring the plus 7 that's out to the side. So you'd have x minus 3 quantity squared if you factored that, and then still have the 7, and then subtract 9, and have minus 2 there, so you'd end up with the same result if you did it that way. Or you could even think about, okay, well, to complete the square here, I know I need 9 units, so let's just add the 2 more units that I need, and then together my 2 plus 7 that I already had would give me 9 units. And then you could factor it into x minus 3 squared and subtract 2 from both sides and end up with the same result. So there's a little bit of slight options there when it comes to completing the square and putting it in vertex form. All right, now that it's in vertex form, however you got there, we're going to graph it with your vertex being at 3, -2. So let me draw on my axis of symmetry, and then as always we're going to need some more points, so let's pick some x values that are kind of close to our vertex. I'm going to go 1 and 2 and plug them in. You could plug them into the vertex form equation or the original standard form equation. I'm just plugging them into the original. We're going to end up with 2 when we plug in 1, and if I plug in 2, 2 squared is 4 minus 12 plus 7, you're going to end up with -1. As I go to plot those, I realize I put 3, -2 at the wrong spot, so let me fix that real quick, and then graph the rest of those points, reflect them over my axis of symmetry, and I've got my graph of my quadratic function. I am also supposed to give the intervals on which my function is increasing and decreasing, so reminder, it's increasing if my y values are rising, if it has a kind of positive slope. And I always specify those using my intervals of x values. So starting at the x value of 3, and for the x values larger than that, my y values are getting larger and larger, so my function's increasing, so from 3 to infinity. And then it's decreasing on the other half, where my x values are less than 3. So from -infinity up to 3, it's decreasing, and my y values are coming down. Now I'm going to find the vertex and x and y intercepts without graphing. Looking at this one, my vertex is translated left 3 and down 5 units from my parent vertex, so it'll be at -3, -5. Now if I'm thinking about x and y intercepts, any point that is on my x-axis, we know the y-coordinate is going to be 0. If you think about a graph, if I'm trying to find the coordinates where it crosses the x-axis, I don't necessarily know the x-coordinate until I do a little bit of work, but I know that the y value itself of that point is going to be 0, and I should have maybe a couple, not necessarily. Could be 2, could be 1, could be none, but could have up to 2 x-intercepts here. So if I'm going to find my x-intercept, let me plug in 0 for y, and I'll solve for x. So I'm going to add 5 to both sides. And then I have the quantity x plus 3 squared equals 5, so take the square root of both sides. Don't forget you have positive and negative square root 5 when you do that, and then equals your x plus 3. Getting x by itself, subtract 3, so I'm going to write it as -3 plus or minus the square root of 5 equals x. And now that's really 2 different x-intercepts. One is the point -3 plus square root 5, 0, and one is the point -3 minus square root 5, 0. So my little sketch up here is just not accurate. I was just showing you, just heads up. Y-intercept wise, if you think about a point on the y-axis, I know the x-coordinate is going to be 0, and I'm trying to find y. So let me take my function and plug in 0 for x. If I do that, I'll have 0 plus 3 squared minus 5. 3 squared would give me 9, minus 5 is 4. So I have the y value of 4 for my y-intercept. So the point 0, 4 is my coordinates where it's going to cross the y-axis.